One and all, is my voice clear? And the video? Please say. So let us begin our today's session. So do you have any queries on the previous class to anyone? Any doubts you can ask. Then let us begin our today's session on normal subgroups. So the definition is we take a group G and H is subgroup of G. We say that the subgroup becomes normal subgroup if it satisfies a property. The property is you take any element in the subgroup H and you take the elements X and its inverse in the group. So if you multiply the product X, H, X inverse, the result must belong to H. So please check out the condition one more time. What it is? You take an element H belongs to H and you take the elements X and X inverse in the group. Now you consider the product of these three values X, H and X inverse, then the result must belong to the subgroup H. If H satisfies this property, then we say that H is normal subgroup of G, and we write it symbolically as H is normal subgroup of G like this. Okay, you please take a note of it. X is outside of H, please understand. From the diagram, X is outside of H. Is that clear? So you take the values X and X inverse in the group which are outside of H, and you are taking only one element H in the subgroup and you are considering the product of it. Okay? Fine. Now, if you look at the properties of normal subgroups, as we know, for every group there will be two subgroups. Always, identity and the group itself. These are again the normal subgroups. So for every group, the default subgroups are nothing but identity and the group itself. They again become the normal subgroups. So for every group, there are two normal subgroups, identity and G itself. They are called as trivial normal subgroups. So if you take any normal subgroup in between these two, bigger than the set identity and smaller than the total group, this normal subgroup we call it as proper normal subgroup or non-trivial normal subgroup. Is it okay? The definition? Right. And one definition we take that simple group. A group which has trivial normal subgroups. Is called simple group. Yes, for checking the subgroups, we take X outside of G. Please understand, if you take X inside of H, then automatically what happens? Since H is a group, by default, X inverse will belong to H. There is no need to check that separately. So you are checking the criteria. If you take an element outside of H, will X inverse belongs to H or not? You are checking actually. Okay? Clear the idea now? Right. And what is meant by simple group? A group which has trivial normal subgroups only, that we call it as a simple group. So from this very perspective, as per the previous class discussion concerned, can you say what will be the order of a simple group? Can you tell? What will be the order of a simple group? Suppose you have taken a finite group. You mentioned that it is a simple group. So what can we say about the group order? After discussing with Lagrange's theorem, we have solved some problems based on Lagrange's theorem. So from that, can you tell? I will give a small hint for you. This problem we have taken in the previous class. Can you check this problem? This we discussed in the previous class. All of you agree for that? A group of prime order has no proper subgroups. So from this point, what you can say, please understand. First we take a non-empty set. Non-empty set satisfying some conditions will become a subgroup. Subgroup satisfying the additional property will become normal subgroup. This is the actual hierarchy if you think about the structure of the subgroups or normal subgroups. So what happens? If you take a group of prime order, it has no proper subgroups. So at this level, you have only improper subgroups. So if the subgroups are improper, by default, normal subgroups are also improper, the next level. So what happens if you say order of the group G is equal to 11, then since it is a prime number, it has only subgroups 2, which are nothing but identity and G itself. You cannot find any other subgroup for G. Since these are trivial subgroups, these are nothing but the trivial normal subgroups. Therefore, this type of group is nothing but a simple group. Okay? Because since the subgroups are improper, normal subgroups are nothing but improper. If you say that apart from trivial subgroups, G will have proper subgroups also, then in that case, you need to check whether that proper subgroup is going to become normal or not. That was the whole idea. That is not always true. One checking condition is, if you take a group of prime order, by default it is a simple group. There are other groups also having different order. But one justification that we can immediately say that if you take a group of prime order, it is nothing but a simple group. So always there will be subgroups which are not normal subgroups, because if you take the case of matrices, there you will find subgroups which are not normal subgroups. Please understand that from the very property, normality is nothing but satisfying the commutative property. Please understand. Normality is nothing but satisfying the commutative property. Since matrices will not satisfy the commutative property, so in matrices, we will find subgroups which are not normal subgroups. Okay? Is that clear? Any questions? So we will have the discussion that if you take a group of prime order, it is simple group. There will be simple groups of having composite order also. That is also correct. While doing the next level chapters, we will discuss. There will be group orders having composite number and they are simple groups. And every subgroup need not be a normal subgroup. So there will be subgroups which are not normal. Yes, every normal subgroup is an abelian group. They will satisfy the commutative property. Okay? Is it clear for you? In fact, from this discussion, we can deduce one small result that you take a group G, it is abelian group. In that case, if you take any subgroup, it will become normal. So every subgroup of an abelian group is normal. You take a note of that we discuss now. After noting, please tell. Have you noted that? Every subgroup of an abelian group is normal. A simple group need not be abelian. A simple group need not be abelian because suppose you just take singleton set identity. It is a group. Is it abelian? If there are two elements, you can check for abelian. If there is only one element, you cannot say about that, right? So by default, abelian property is satisfied there. How its trivial group G will be normal? So let me say, if this is the group, it is by default normal because it satisfies the property that consider x e x inverse, this is nothing but x inverse, nothing but identity. That's it. It is satisfying the property x inverse belongs to H. So here H is any element. So here you are having only one element. It satisfies the normality property. Please understand. It is by default abelian. It always satisfies the commutative property with other elements of the group. That means how G becomes normal to G, isn't it? Is that your question? How G is a normal subgroup of G itself? Right. Now you take the graph as it is. First of all, G is a subset of G, that we agree, and G is a subgroup of G. You accept it? Because G itself is a group. Say, right. Now we check for normality. Since you are taking the elements within itself, X, H, X inverse, all the elements belong to G. So by closure law, the product also belongs to G. There is no need to check separately because I have taken all the three elements within G only. I didn't take any element outside of G. Are you getting? That's it. So by closure law, we say that X, H, X inverse belongs to G. Therefore, it is a normal subgroup. Right. So you are saying that normal subgroup means it is abelian means. So you are saying that if G is a normal subgroup, so G may be abelian, G may not be abelian. That cases will exist. That is actually you are saying, right? Now I got your point. Right. I got your point. So here we need to understand that normal subgroup satisfies the commutative property with the other subsets of the group. I want to finish the sentence. Normal subgroup satisfies commutative property with other subsets and other subgroups of the group. That is the specialty of it. The special property it has is, if you take that H is a normal subgroup and say N is any subset of G, so immediately we can say that NH is equal to Hn. This type of abelian property I want to discuss. It commutes with every subset of G. This is the special property of the normal subgroup. That you take a note of it and we will have it. So if G is not abelian, how G will be? Please understand, normal, you cannot straight away say that normal means by default abelian. Don't mistake me. So my intention is, it satisfies the commutative property with other elements. For the subgroup I am saying, not for the group. Please understand. For the subgroup I am saying, not for the group. Because our discussion is confined to subgroups only. You have learned all the groups in a separate manner. So don't compare the two things, group and subgroup. So you forget about the group thing. We discuss the concepts with regard to subgroup only. Right? So where are we? Yeah. So we have taken that G is an abelian group and H is, then if you take any subgroup H, then H is nothing but normal subgroup of G. That is the thing we need to understand here. So every subgroup H of an abelian group is normal. This is the statement. Clear to all? Now let us discuss with this. So you take the usual diagram. I have taken H belongs to H and X inverse belongs to G. Now I have to prove that X inverse belongs to H. This is my intention. Now you consider the value X inverse. So this can be written as X inverse H. Why? Because for these two elements, I have applied the commutative property because G is abelian. Because basically all the elements belong to the group. Since it is abelian group, the elements will commute. So I can say Hx inverse is nothing but X inverse H. So applying associative law here, you can write like this. So this is nothing but identity into H equal to H. So I can write like this, equal to H. So this value belongs to H, as you have taken H belongs to H. Therefore, X inverse is belonging to H. Therefore, H is a normal subgroup of G. Okay? Take a note of that. After noting, please tell. Right. So there are certain results based on the normal subgroup. From the very definition of normal subgroup, we need to understand that H normal subgroup of G means X inverse equal to H. This is the fundamental thing we need to understand. If H is normal subgroup of G, then X inverse equal to H for every element X belongs to G. This is one result. Another result is H normal subgroup of G if and only if every left coset equal to right coset. This is one good result, we will prove later. Another one is H normal subgroup of G if and only if product of two left cosets is again a left coset. This is also true for right cosets. You take a note of these values, in which we are going to discuss this result. H is normal subgroup of G if and only if every left coset equal to right coset for the same element. After noting, please tell. So here it contains main part as well as converse part. Suppose we take the main part. Say H is normal subgroup of G. So what we have to show? Every left coset equal to right coset. From the very definition, we know that normal subgroup means XH X inverse equal to H. So to this relation, multiply with X both sides. I am doing the post multiplication. So XH X inverse X equal to HX. So this part is nothing but identity. So this implies XH is equal to HX. So every left coset is equal to right coset. Is it clear? Now let us go with the converse part. Please take a note of that. I'll take the converse part. Fine. So, on the other hand, you take that every left coset is equal to right coset. Now, let us take X belongs to G, and we have XH is equal to HY. Because every left coset is equal to right coset. We don't know whether XH equal to same right coset or another right coset, we don't know. So as per the assumption considered, we are taking that left coset equal to right coset. Okay. Now, can I say that X belongs to XH? Do you agree for this value? X belongs to XH. That means whenever you are writing a coset, here the coset is generated by the element X. So by default, X should be there in that coset. If you have a doubt, you have constructed so many cosets in the previous class. Suppose you have taken the coset 1 plus 15H. This coset always contains the element 1. So if you take the coset 3 plus 15H, it always contains the element 3. Could you check on that? All of you? So we know that X belongs to XH and this is equal to HY. So X belongs to HY. Yes, we can take E in H for that, right? So in cosets chapter, I have given certain results that A belongs to HB if and only if HA is equal to HB. Could you check on this result? I have given the results for you in the previous class. This type of result we have mentioned there. Can you check? So, based on the result, applying here, we can say that X belongs to HY if and only if HX is equal to HY. So if you combine these two results, we can say that xh is equal to hy, this is equal to hx. Therefore, xh is equal to hx. Please check on that. So, from this relation, if you multiply both sides with x inverse, you will have xh x inverse is equal to hx x inverse since xh x inverse equal to h, from the first equation what I have written, h is normal subgroup of G. This is about the converse part. So what is the overall ideology in converse part? I have taken that the left coset is equal to some right coset. Using the result in cosets, I concluded that xh is equal to hx. So left coset, right coset are same for the same element. So multiplying both sides with x inverse, I got the if and only if condition. From this, I say that immediately h is normal subgroup of G. Okay? This is the proof of the result. You please take a note, then we discuss the other interesting result, which is also given in the previous year papers. If any questions, you can ask. After noting, please let me know. Please understand, if you observe the concept of coset, a coset will be formed by taking every element in G. Just we are talking about the finite groups. Don't think that G is infinite. So whatever the finite group you consider, for every element in G, we can calculate one coset with respect to the subgroup H. So here what happens, as we have done a good result that xh is equal to hx is equal to h, if and only if x belongs to h. This kind of result we have studied in the previous class. So it means that while forming the cosets, the element which we have taken in G is also a member of H. In that situation, there is no distinction between the coset and the subgroup. Both are equal. So, while considering the coset, generally we take x outside of H. You can take x inside of H also, but it is nothing but the subgroup itself. As per this result is considered. We have proved that already. So the element may be within H or outside H. Both are applicable. Don't stick on to one end. You can take X on any part of it. Fine. Any other questions? All right. So based on your context only, we will prove the following result. The question what we have raised now. There is one good result based on this. You please take a note of it. It is also given in the previous year papers. So you take a group G and H is a subgroup with index 2 in G. So we have to show that H is normal subgroup of G. That is the statement. So please take a note of this statement. Is coset a group? So if that is the case, you check with the necessary and sufficient condition. So as you are mentioned that X, H both are becoming equal, in that case, it is a group. Why not? The very best example is if you want to conclude the result, let me say. 1 plus 15H, this coset we have calculated. Could you give me the value here for that problem? This is the coset, am I correct? There we have calculated the problem. Z15 plus 15, say. Right. Now see, if you want to check that whether it is a group or not, first of all, let us check for the closure law. Now you take these two elements, you simply add them up. 11. Is this value belong to the coset? Therefore, it is not a subgroup at all because the closure law is failed. So, coset may be a subgroup or may not be a subgroup. You cannot decide. If you want a counter example, this is the counter example. Clear now? Right. So, what is the significance of this coset? If you ask, let me say, why we are doing like this? Suppose you consider the space R square, the two-dimensional space. If you take the operation plus, let us take, if you take the ordered pairs A and B, you are simply adding them. You are simply multiplying them. Let us take whatever the case. So here, origin acts as identity. So if you talk of subgroups, then a subgroup is a line passing through the origin. You consider distinct lines. The lines which are passing through the origin are nothing but the subgroups. If you want a geometrical view for your understanding. And what is meant by a coset? As you have taken 1 plus 15H, so it means that for this subgroup H, you are adding 1. So this is a line parallel to H. So you are considering the parallel lines by taking a fixed subgroup H. Okay? Clear now? So from that geometrical perspective, you can say that coset is not a group because it is not passing through the origin. So it is not containing the element identity origin. So it cannot be a subgroup. Right? The geometrical view that can imagine like that. If you call upon the 3D perspective, suppose you have taken R cube, the three-dimensional space you consider. So in the three-dimensional space, subgroup is nothing but a plane passing through the origin. So subgroup is nothing but a plane passing through the origin. So if you talk of cosets, a coset is another plane which is parallel to the fixed plane what you have taken. So you fix one plane, you are considering the set of blocks which are parallel to this plane. That is nothing but the coset. Okay? Right. So as per the discussion, please understand, if you take x belongs to h, hx is equal to h always. So h is a group because these two are becoming equal. You cannot find a different set other than h. H itself is by default a group you have taken. So that the coset is a group. There is no distinction between the coset and group if you take the element in the subgroup itself. It is nothing but the perspective you are writing the line overlappingly like this. Because the same coset is nothing but the group itself. Okay? Right. Any other questions or doubts? Fine. Now coming to the problem, the result what you have taken here. So this is the result we have considered. If G is a group and H is a subgroup of G with index 2, then we have to show that H is normal subgroup of G. Now first of all tell me what is meant by index. What is meant by index? Can you recollect the definition from the previous class? Very good. Order of G by order of H. That's a nice response. From this, what we can understand? Order of G by order of H. As we know, you are going to calculate the number of cosets basing on H from the elements of G. So here, after calculating the cosets, some cosets will get repeated. And the total distinct cosets you calculate, that we are calling it as index. So we are using the symbol order of G by order of H. So if I say that order of G by order of H is equal to 5, it means that I will get 5 distinct cosets among all the cosets. So remaining are becoming equal. Agree? So from this problem, since index 2 is given that, so you will get exactly 2 distinct cosets for the subgroup H from the group G. So you can consider the coset as left coset as well as right coset. So here what happens? HE, HX are distinct right cosets. If we have written left cosets, EH, XH are distinct left cosets. Apart from this, you will not get any other coset because index is 2 only. Whatever the coset you consider, that is becoming equal to either this or this. That's all. So if you calculate any left coset, that is becoming equal to this one or this one. That's it. So if you take an element X belongs to G, then these are the only right coset and these are the only left cosets. From the data, index 2 is given. Are you clear? Yes or no? Any other questions from anybody? for this point? All right. Now, as one of our friends asked earlier that, can we take always X beyond the set H? There is no need at all. So here, while calculating the coset, I have taken X belongs to G. So here you will get two cases. The element X, which is taken by U, may belong to H. The element which is taken by U may not belong to H. These two cases would exist here. So in the two cases, whatever the case you consider, we have to prove that H is normal subgroup of G as per the objective of the result concerned. Fine. So you take the first case. X belongs to H, you consider the case. Immediately, as per the previous class, we can say that XH is equal to H is equal to Hx. You agree? Right. So from this, you can say that XH is equal to Hx. Left coset is equal to right coset. And in the beginning of the today's session, we have discussed three results. 1, 2, 3 for proving that it is a normal subgroup. All these are nothing but if and only if conditions. So since left coset is equal to right coset, immediately we can say that H is normal subgroup of G. Clear? Take a note of that. Now you take the second case, X is outside of H. Now what happens? As we know, these are the only distinct right cosets. These are the only distinct left cosets. And as per our observation on cosets considered, if you consider the union of distinct cosets, it is giving the whole group G. Agree? You have written the group also. Did you verify or not? So from this you can say that you can write G is equal to HE union Hx if you write the right cosets, and you can write G also as EH union XH. So G can be written as union of left cosets, G can be written as union of right cosets. You can consider any type of coset, that is up to your possibility. So for the value G, you got two representations, representation 1, representation 2. Therefore, these two must be equal. Since these two are same sets, so these two must be equal. Since left coset is equal to right coset, immediately you can say that H is normal subgroup of G. So while proving that H is normal subgroup of G, our main intention is nothing but showing left coset is equal to right coset. That is our ideology to prove that. So whatever the case you consider, our strategy is to show that left coset is becoming equal to right coset so that H becomes normal. That's all. Is it fine? That is the solution of the result. You take a note of it. how to imagine normal subgroup like coset. Don't misunderstand the thing that subgroup, normal subgroup in one way geometrically same. Please understand, normal subgroup is not something separate. If you take a subgroup, it is having some extra property. That is why we are calling it as the normal subgroup. As you know, subgroup is nothing but a line passing through the origin. So the special quality of the line is it is commuting with the cosets. Left coset, right coset are becoming equal for that set. That is the specialty of it. That you can imagine geometrically. So don't separate that subgroup and normal subgroup are totally different. You see the hierarchy. I took a non-empty set, a subset satisfying some properties becoming a subgroup, and a subgroup having additional property becoming normal subgroup. It is just like adding one after the things. That's all. Nothing something special. Okay. So there will be no visualization. A proper normal subgroup simply means an abelian one. That we have to check it out. We should take an example and we have to prove that. So one interesting thing I want to say about abstract algebra is, as you know, fundamentally some definitions and theorems, while observing the technical terms, we will get a lot of questions. Very interesting questions we will get. So you will take one technical term from the theorem, you take another technical term from the other theorem. Can you correlate them? Can you draw any new conclusion out of this? You can conclude them and you can have your own logic. But the practical problem is, if you want to give a justification for a statement, you should have a strategy. That strategy must be approved by everyone. If at least one counterexample is there to show that your strategy is wrong, the whole effort will be a waste. Please understand that. Please understand that. That is the problem with abstract algebra. Now, immediately I can ask one thing that, now see, as we have discussed normal subgroups, I have given a group order to you. Immediately you should ask one question. How many subgroups I will get for a group? How many normal subgroups I will get for a group? Immediately on seeing order of the group, can I say that how many normal subgroups will be there and subgroups will be there? And can I say that it is a simple group or not? How can I verify that? Suppose if I say that this is a subgroup, then immediately without judging them, how can I say that how many elements will be there in that subgroup, etc., etc. This type of questions will come into our mind immediately. We will get a lot of questions. I accept and appreciate your enthusiasm. The thing is, once you go to the high level chapters, then we will go on to solve all these of questions. Because at that level only, we will understand the total nature of abstract algebra. Okay? In exam, how will mention known results? It is just like simply write the statement of it. That's all, nothing enough. There is no need to write the proof. There is one good part in abstract algebra is, if you recollect the result, it is okay. Otherwise, simply you mention by known result, this is correct. You simply write, that's it. The examiner will evaluate you whether it is right or wrong, because he knows whether such results exist or not. That is the best part of abstract algebra. So you are asking about the sins. If I didn't write the exact sins, what happens? Or if I fail to represent the total sins condition, what happens? If that is our question, you simply mention that by known result, left coset is equal to right coset, hence it is a normal subgroup. That's all. That is enough. There is no need to write the entire content of the statement. There is no need of it. Exactly. We have too many definitions and results also in abstract algebra. That is the problem with it. That is the problem with it. Except that you cannot skip a step. There cannot be any mistake in presenting the solution, because it is purely based on the logic, not of any formula. The error part is very less if you recollect the logic at that moment. Okay? So you come up with your questions. I will like most of them. You come up with your questions. Fine. Now, the result is just what we have discussed. Is it fine for everyone? Did you get the overall idea? How we are proving this? So, I will say one thing. As we have taken the syllabus part in the orientation class, the total abstract algebra is mainly bifurcated into two parts: groups and rings. Actually, fundamentally, these are totally different in nature. So, in groups, you will take only a set and you will take only one binary operation. Based on this, you are verifying all the properties on this set. And you are classifying groups, subgroups, normal subgroups, etc., etc., etc. If you take the case of rings, you take a set R. Here you will take two binary operations. Whatever the properties you are checking, closure, associative, identity, inverse, you are checking for two binary operations, not for single. Let me say, if you take the integer set is satisfying all the four properties: closure, associative, identity, inverse with respect to plus. So Z comma plus is a group. Now you are taking the second operation dot and you are checking with respect to dot how many operations are satisfied by Z. So based on that, you are classifying whether it is a ring or not. So you are checking the properties or laws with respect to two binary operations and a single set. And there you will get subrings, etc., etc. So here you will get normal subgroups. There we use the technical word ideal, etc. will come. So the innermost nature is very simple and very similar. There will be no interconnectivity. But if you understand group theory correctly, then ring theory is nothing but a cakewalk for you. Only you will know the technical terms. That's all. Everything is very easy because the same type of logic you are going to apply here. Nothing different. The verbatim is different. The technical words or glossary of terms what you are using here is different. That's all. The inner logic is same. So initially, groups takes much time because it involves so many concepts. Once you finish the groups, rings is very small because the same concept you are rechecking here with another operation. That's all. Okay? Does it sounds good for you? And one interesting thing, if you ask, the length of the solution in groups is small, but in rings, since you are doing with two binary operation, length of the solution is somewhat bigger. That's it. Fine. Thank you for your good listening. So after coming this, we can say one more thing, that intersection of two normal subgroups is again a normal subgroup. Intersection of two normal subgroups is again a normal subgroup. It is very easy proof. Can you try? If you understand how to prove intersection of subgroups is a subgroup, the same kind of logic we apply here. I will show you. First of all, let us take H comma K are two normal subgroups of G. So basically these are subgroups. And they are normal. So our claim is to show that H intersection K is normal. So what is the pattern? Non-empty, subgroup, normal subgroup. This is the hierarchy to follow. Agree? Yes or no? Right. So fundamentally, you can say that so we know that the intersection of two subgroups is a subgroup. So first part is clear, second part is clear. We have to go for third part. So let us go for it. So if you say let x comma x inverse belongs to G, let y belongs to H intersection K. It is very simple proof. Please check that. What you said, I have written on board. Would you agree? That's it. So, in the exam point of view, if you consider, if the question is given for 10 marks, this is the only solution. If the question is given for 10 marks, this is the only solution. 1, 2, 3, 4, 5. 5 lines is the solution. If the question is given for 15 marks, so in order to get the thing, as you have mentioned, intersection of two subgroups is a subgroup, that you are going to prove it again. This part you have already done. Can you recollect the proof right now? It is also a 5 lines proof here. There we will prove that AB inverse belongs to H intersection K. The necessary and sufficient condition we will consider there. Could you recollect that condition? While proving that intersection of two subgroups is a subgroup, we make use of this condition. Accepted? So, if the question is given for 15 marks, then this is 5 lines proof, this is 5 lines proof, total 10 lines we will write. That's it. He will be given 15 marks. Now see the difference. So, with regard to the weightage of the question, we can manipulate the solution, how much you can write. If the weightage is less, you just write 5 lines, you will be given full marks. If the weightage is more, you have to add up some more result here, which adds some other lines. That's all. But both have the similar logic, you should agree. The logic what you have applied here, the same logic we have applied here also. Fine. Now let us take one more problem, which is also a previous year question asked in the papers. So this is one good result. You please take a note of this. We will discuss with the approach. If you get the logic, writing the solution of this result is very easy. Otherwise, you will get more confused after looking at the solution. However, I will draw the respective pictures for you also to get good understanding over that. So what it is given in the problem, I took two normal subgroups for the group G. And what is one additional quality of the normal subgroups? If you consider their intersection has only one element, E. So in one way you can say that they are totally disjoint sets. There is only one element common, that is identity. So you have to prove that every element of M commutes with every element of N. So what is meant by commuting? Commuting is nothing but satisfying the commutative property. So if you say, I took an element M belongs to M, I took an element N belongs to N. So our intention is to show that Mn is equal to Nm. This is the target of the problem. That is our main wish, to show that every element of M commutes with every element of N. Okay? Is that clear? Now, the ideology is very simple. Since it is given that M intersection N is equal to E, see, so if you observe that this what we have to show. Now, if you bring these elements this way, they will become minus. Inverse part you will get. So I want to show that N, M, N inverse, M inverse belong to M intersection N. This is my claim. So I have to show that using the property of normal subgroups, I want to show that the element N, M, N inverse, M inverse is belonging to the intersection. Okay? Are you clear, everyone? Fine. Basically, all these elements belonging to the group. Basically, all these elements belong to the group. Now, I will say like this. You please check the result, what I have written. So if you want a systematic diagram, this is the diagram for what I have written. Initially, I have taken N here. By inverse law, N inverse belongs to N. By normal subgroup property, I can say that M, N inverse, M inverse belongs to it. And since these two are belonging, you can say like this. This is the diagrammatic representation for the matter what I have written here. Do you agree? Any queries for anybody? Please tell. Anybody has any queries? Please tell. Now, let us take the other part. Agree? For the top 3 lines, what I have written? Therefore, this is the element which belong to the both sets. So it belongs to the intersection. So you have n, m, n inverse, m inverse belong to the intersection. In the problem, it is given that intersection is nothing but a single element identity. So this element must be equal to identity. It has no other option because the set contains one and only one element. So n, m, n inverse, m inverse equal to E. So if you multiply both sides with m, you will get that E into m. If you multiply both sides with n, that's all. Therefore, nm is equal to mn. Every element commutes with other element. Therefore, the task is finished. That is the very logic. Please check out the logic, how it is proved. This is our actual claim to show that initially I have taken the claim that n, m, n inverse, m inverse belong to m intersection n. For that, I took the element individually to show that it belongs to n, it belongs to m, using the properties of normal subgroup, closure law, and inverse law. Hence, I have solved the problem. Any questions or any doubts for anybody? Please ask. Please take a note of this. Then if you are clear, I want to give 1 or 2 definitions. Then let us conclude our today's session here. Then tomorrow we will meet. Because all these results will give you a boredom with regard to normal subgroups and abstract algebra. I hope. After noting, please let me know. All of you clear? If you want me to explain the result again with diagrams, I will explain that. Shall I? Is that required for you? Please tell. The result what we have considered now, you want me to show diagrammatically the steps one after the other? Right? Then see, you can imagine the first diagram like this. As I have taken the element n belongs to n, its inverse also belongs to n. This is the first step. Agree? Because there is the inverse property, right? The second step, if you observe, this is my diagram. What I have taken, this is the thing I have taken. Here I have taken n inverse, m inverse I have taken. Since it is normal subgroup, n inverse, m inverse belong to n. Observe the second step. The property of the normal subgroup I have applied. Any questions? Is this picture clearly gives the idea or not? Everyone, right? So third step, if you observe, I used the closure law. So closure law is nothing but I have taken the set n. It contains two values. One value is n, one value is. So the product will belong to the set by closure law. So first I used the inverse technique, then I used normal subgroup technique, then I used closure law. Whenever two elements are there in the set, the product is also belong to the same set. This is the way I have shown that n, m, n inverse, m inverse belongs to n. The similar logic I have applied for m also. Is it clear now? If anybody has any other queries, please ask. Because your response is more valuable in getting the context. Based on that only I can understand in what way you are thinking. So there is one element which is common to both the sets, hence it belongs to the intersection. So it must be equal to the only one element there. So multiplying both sides with m inverse gets cancelled. Multiplying both sides with n inverse gets cancelled. This is the thing we will get. Is it clear now? If any doubts come, you ask. So can I erase the result here? You please take a note of the pictures which are there for your understanding, which gives the overall idea. So without these pictures, if you read the content, you will get confusion. How these are written actually. We agree? No. Please understand that intersection is equal to identity is already given in the problem. This is the hypothesis of the problem. Have you noted that? So the actual claim of the problem is nothing but showing nm is equal to mn. So let me say, I will draw the picture here which gives the overall view. So actually, I have given a group G. It has two normal subgroups, m and n. The intersection of these two sets is nothing but only one element, E. So except E, there is no other element in the intersection. This is the actual data. And what is the question part? it is given that you take an element in M, you take an element in Y, these two commute. This is the question part. This is actually we have to show. So for this, I took M in the set M, I took N in the set N. So as per the problem asked, I have to show Mn is equal to Nm. Clear? Are you clear or not? The objective. So the only special property I got here is nothing but the intersection is having only one element. This is the special property. I have to make use of this. That's why I used the technique that I want to show N, M, N inverse, M inverse belong to the intersection. So for this, individually, I have shown that this value belongs to M, this value belongs to N using the properties what I drawn here. So what happened? If this value belongs to the intersection, nothing but only one element, this must be equal to this element only. It has no other choice. So that this thing will come. So by multiplying both sides with M and N, you will get this result. Now the picture clear. Now the picture clear. Why I have taken this big element belong to the intersection? Everyone. Now you please ask your questions if any doubt is there with regard to this result. Don't hesitate to ask. I will wait here. That is the overall view for the problem. So initially I felt that after reading the problem statement, you have identified the objective of the question. That's why straight away I went to the proof. This is my actual aim. But the intention of the problem is like that. If you take one element in M, one element in N, they will commute. It is true for every element. You can take any element in M, you can take any element in N, they will commute. Now you can understand that as one of our friends asked that is normal subgroup abelian, so it is satisfying commutative property with other sets. You can understand? They are satisfying the commutative property with other sets. That's it. Any more questions you have on this question? Please let me know. So if your idea is totally clear, then I will end up our today's session. We will meet tomorrow. So I want to mention one more thing that with regard to your preparation as per the abstract algebra is concerned, I will take maximum the total coverage of the syllabus as well as previous year questions as per your listening is concerned. So for your view, you can say that you can follow any standard textbook for the revision purpose. The class session is good enough for you to understand the total syllabus and total content, right? So for revision purpose, you can follow any textbook. So I will take up to 90 to 95% of the coverage of previous year questions in the class itself. So class notes is sufficient for you. But it takes some more classes. Minimum 50 hours we need to consider for the completion of abstract algebra. Okay? Is it comfortable for you? I have given the list of textbooks in the orientation class. You can follow Abstract Algebra by S. Chand, Sham series, Modern Algebra by Krishna series, or V.K. Khanna, S.K. Bombri, Abstract Algebra. Several books are there, you can follow any one book. Abstract Algebra by Joseph A. Gallian, that also you can take. And P.B. Bhattacharya, Abstract Algebra by P.B. Bhattacharya, that also you can take. Right. Any other doubts, please? Thank you.